All right, and welcome back. And so what we're about to do now is to try to continue exploring one-dimensional kinematics. We have a very good handle on what that covers, but we want to go into a different dimension this time. And so previous to this, we've covered one-dimensional motion in the horizontal direction. But now what we're going to do is specifically concentrate on 1D motion in the vertical direction, straight up and straight down. And the key to understanding what we're about to do is to make a couple of assumptions. First of all, that all of our objects, they're either going straight up and straight down. They do not have any sort of horizontal component. And so, yeah, we go up, we come back down, maybe we're just dropping something, maybe something's being thrown straight down. That was more of a drop again, thrown straight down. Like so. These are the types of questions we're dealing with. They do not have any kind of horizontal motion. If I wasn't going straight down and I had a little bit of a angle in the horizontal, that's a different type of motion. Then we're getting into what's called projectile motion, and that is a more advanced topic for a later time. So if we're just dealing with one-dimensional motion in the y direction, you might be saying to yourself, well, isn't that just the same thing as the x? How is that different other than us using a different letter for our values? Essentially, you're right. The one thing that we will assume is that all of our one-dimensional kinematics in the first year physics will assume that you're on the surface of the Earth, or very close to the surface of the Earth, so that in fact, we already know what the acceleration of that one-dimensional motion is in the y direction. Of course, it's due to the acceleration due to gravity, of course, yeah. And so that value is well known. I mean, if there was no gravity in this room right here, obviously this ball would not fall in the downward direction. It is given an acceleration due to where it is. And I assume that all of you are also watching this video from the surface of the Earth. If not, it actually is not that hard to change what we're about to do for other planets. So if you were on the moon or on Mars or somewhere else, the acceleration due to the Earth's gravitational field can just be replaced with whatever gravitational acceleration that you are under. All right, so what do we call all of this? What's this sort of one-dimensional kinematic motion in the y direction called? We call the whole thing free fall. So that's what we're studying now, free fall. Now for us in our everyday kind of logic, we see the word free fall and we think of falling, just falling. And so this certainly would qualify as free fall, but there's other types of motion as well that's more than just dropping. Dropping something is clearly free fall, but it turns out that free fall covers not just the motion of something dropping from rest. Let's say a can of pop rolls off of a, that's not a great example. Let's say an acorn falls out of a tree. That's free fall for sure. But it's actually any type of motion of an object that is in the vertical direction near the surface of the Earth. And so it actually doesn't even have to be going down. You can absolutely be going up and still be under free fall. I'll show you what I mean in 1 second, but let's define this as the motion of an object under the acceleration due to gravity only. Now you could consider objects that do move in the vertical direction that do not travel under gravity only. Rocket ships, for example, when they first launch, or even drones. Drones are another good example. Hummingbirds. There is obviously some other acceleration in the vertical direction that is driving them to oftentimes go up instead of down, or to go down at a different speed, etc. And so it's not that hard for us to deal with those types of problems once we've done free fall with gravity only. And so for now, we're going to stick with gravity only, keeping in mind we could go to other types of accelerations without too much trouble at all. And so when we say the vertical direction, I mean only what we will call the y direction. There's no x motion at all. Okay, so let's make sure we understand what free fall is by looking at a few examples, and I've filmed a few examples of free fall for us to look at. Okay, so in this video, keep an eye on the various types of motion that occurs. Let's see what happens. Okay, so that was your typical drop. That is free fall for sure. And here we are throwing a ball in the upwards direction. Eventually gravity does drive it back down. And then once again downwards, but this time not dropped, but thrown down. In each of these circumstances, the initial conditions are different. Sometimes our object has no velocity. When you drop something, it has no initial velocity, and then gravity is what's deciding what its subsequent motion is. If you throw something straight up in the air, same thing happens. It's gravity that decides what happens after the initial throw. Sure, you have some initial velocity in the upwards direction, and you look at it and you're like, well, that's not free fall. It is absolutely free fall because the gravitational acceleration is acting downwards. When we throw something up in the air, the reason it comes back down is because gravity is driving that object towards the ground. So it'll slow down, slow down, slow down, go to zero, and start speeding up as it comes down. And then finally, if I take an object and I throw it on the ground, yes, I'm giving it some initial velocity in the downwards direction, but any subsequent motion is due to the acceleration of gravity. Let's look at the same kinds of drops, but in slow motion this time. And so we'll see for ourselves here. There we go. This is our first drop. I want you to look at the tennis ball falling slow. Look how slow it's going initially. And as it gets closer and closer to the ground, you can see that it's covering more time per second. That is, the distance per second is increasing. So it is accelerating. The velocity is going up. The same thing is about to happen with this ball here. This ball is about to be thrown straight up with some significant speed. And as gravity's acceleration works on it, it gets slower, 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 stops, turns around and starts going downwards. Faster, 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 faster. And as it reaches the same height that the hand threw it, it's actually going the same speed, but in the downwards direction. So if you throw something up with 5 meters per second, it'll come back down at that height with the same speed, and then continue to get faster and faster and faster and faster as it heads towards the ground. And finally, we can throw this one straight down with some initial velocity in the downwards direction. And so it's going to speed up still, but it already started with a faster speed. Because this one is already moving faster when it started, once it hits the ground, it's moving even faster than the one that we dropped. All examples of free fall. Okay, so that was very exciting, I think, and what we have shown is that in all of those cases, the acceleration is in the downwards direction. Doesn't matter if you drop something, throw something up, throw something down, gravity is accelerating that object downwards. And so how fast is that acceleration? It's given by a constant. It's not a universal constant, but it's a very functional constant of lowercase g equals 9.80 meters per second squared. This is defined as the acceleration to three significant figures of the acceleration due to gravity near the Earth's surface. And so if you are very, very far away from the Earth's surface, that number will change. But that's not what we're going to be covering in kinematics one dimension. That happens a little bit later with gravity. And so now that we've put this value g as 9.80 meters per second squared, we ask ourselves, is this a positive number or is this a negative number? And now for those that may have seen this number before used in high school, we often mistakenly think of g as negative. It is not negative. G is the acceleration and it is a positive number. It's actually not even a vector. It is a scalar, and so it is definitely a positive number. Now the acceleration due to gravity can be negative. You can set a equals negative g or a equals negative 9.80 meters per second squared, but that depends on the setup of your problem. Inherently, the value g is a positive value. Do not put g as negative, because then sometimes you end up saying a is equal to negative g, and then you put in g equals negative 9.8, and you get rid of, etc. You'll see when we do examples that we want to make our acceleration negative in certain circumstances, but g itself remains positive. Let me just write that down symbolically. So for this example, let's say we've got ourselves a cube here, and that cube is falling downwards. So that double arrow there with two lines represents the motion of our block. If you set your positive y direction upwards, which I most often do, regardless of the fact that this object is going downwards, I still like to have y positive up. It helps me do lots of different problems. But it is your choice absolutely whether you set the positive direction of y down or up, but you have to make that choice. You have to do that setting, otherwise you're going to confuse your positive and your negative values. So even in this case, g is still positive 9.80 meters per second squared. It's the acceleration in the y direction that this time has to be negative. Because we said that plus y was positive up, and we know that the acceleration is working in the downward direction, that means our ay is negative g, and this equals negative 9.80 meters per second squared. And so that's how we'll functionally use this acceleration. And overall, I hope what you see when you look at this is free fall is actually easier than one-dimensional kinematics in the horizontal direction. And one-dimensional kinematics in the horizontal direction, we had to have our acceleration as a variable. It could have been a, or it could have been some positive constant or some negative constant, and our problem depended on it. Here, we already know what the acceleration is. We know what direction it's moving, and so therefore we can just basically have less options, less variables, if you will, when we're doing these problems, which should make our problems easier still. An interesting thing happens now that we've established the idea of free fall and we've looked at it with regard to this acceleration due to gravity. We start to wonder about how it affects different objects. Does the acceleration of gravity have a different effect on different mass objects, for example? Intuitively, we want to say yes. We want to say in our experience that heavier things fall faster. But probably through different science courses that you've taken, you know that that is not the case. This was I would say, relatively recent scientific discovery from our good friend Galileo. And so about 450 years ago, the very, very famous Galileo was doing his work on astronomy and on physics, coming up with concepts of inertia and using telescopes for the first time to observe things in our solar system, helping to firmly establish the sun as the center of the solar system. And then at that time, they probably thought the universe. But these great scientific discoveries that he made, on top of that, is the idea that all objects fall with the same acceleration due to gravity. And we can put it another way, and this is coming straight from Galileo. He says that all objects are acted upon equally by the acceleration due to gravity. Regardless of their size, shape, or mass. All right, so Galileo did do a series of important experiments. Traditionally, it's thought that he did it at the Leaning Tower of Pisa, his work on inertia, as well as this idea by dropping things off of the Leaning Tower. Not having access to a Leaning Tower right now, though I do sometimes worry about the foundation of, we try to recreate some of these experiments that Galileo conducted. And so let's have a look. All right, so what we're going to do is to drop various objects from the same height at the same time. Oh, there we go. There's a quick one right there. We're going to see that again in very slow motion. This is another fall that you see. Of course, you can rewind and watch that again, but this is in slow motion now. And so we've got a big basketball of greater mass, a smaller junior-sized tennis ball. It's a little bigger than a normal tennis ball, but a bit lighter. And as we see it falling, they are falling at the same rate. We can watch that one more time. Let's watch both of those again. First, the quick one. Looked like the tennis ball was gaining a little bit there. Maybe it wasn't dropped right at the right time. Maybe, I'm not sure. Let's look at it again slowly. So here, when I look closely, I do see them at the same height. Basically, their center of masses are at the same height. But notice the tennis ball seems to somehow get ahead a little bit. Is it my timing, or could there be other factors involved? Let's take two objects that are much different from one another and look closely to make sure this Galileo idea is in fact true. And so in the next video, we're going to take a textbook. I'll just pause that for a second. And in this video, we've got a textbook on the left-hand side. We've got a feather on the right-hand side. The feather is actually made out of paper, but it's shaped like a feather and it's probably close to the same mass as a feather. We're going to drop both of them from this height. Now, before you get too excited, I'm trying not to be disrespectful to this book. It's a physics textbook, an older edition, and I feel like it's servicing science here. We're putting this book to good use by demonstrating important physics concepts to you. And so the book was fine. Here we go. And please do not try this at home. I'm a trained professional. Oh boy, we got to see that one more time. Okay, here we go. Again, a textbook and a paper feather. And if Galileo's right, they should, oh my gosh. Clearly, the textbook fell much, much faster. It had a higher velocity. It took less long. Let's watch the same thing. Oh, wait. Let's slow this one down. Okay, so we've got something else happening in this video now. So in our first video, what we've shown is that the feather does not seem to drop with the same acceleration as the book. the book was going faster because of acceleration. It took less time because of acceleration. And so what is the factor that we are missing in this idea? Well, it looks as though the paper is influenced by the air, the atmosphere itself. Not that it's super windy or anything like that, but the fact is there is some sort of resistance. And the book doesn't seem to feel that resistance nearly as much as the paper does. The paper tends to feel the resistance more because of how light it is. And so we're going to have to figure out a way to do the same experiment to test the acceleration on the piece of paper and the book without having air be a factor, essentially the air resistance to be a factor. And so we could evacuate all of the air while I'm outside. It would you basically need no atmosphere to do. This experiment would work well on the moon, for example, and it has been done on the moon by astronauts. But there is an easier way to do it than getting rid of all of the air in a room or on a planet. What I'm going to do is I'll put the piece of paper, as you'll see in the video, on top of the textbook. And that way, the textbook will block any air resistance from affecting our feather. Now, if it was the light mass of the feather due to gravity that was causing it not to fall as fast, well, eventually what you expect is that the heavier book would leave the feather behind. Let's see what happens when we conduct that experiment. All right, feather on top, dropping the book, and they fall together. You see it there at the very bottom. And so, in fact, what we have shown is consistent with Galileo, but let's watch it one more time. And we're going to watch this one in slow motion, so we have plenty of time to talk about it. Again, a very, very heavy textbook, a large, solid textbook in one hand, paper feather in the other. They're both dropped at the same height at the same time, and we see a very different reaction. Look how fast the book accelerates until it hits the ground, while our feather has barely moved at all. And there it goes. We're just going to sit here and watch it. It's kind of hypnotic, kind of lovely, actually. It even leaves a screen there for a second before floating. It's still not done. It's still got like a while to go before it hits the ground. Is it there? No, not yet. And so essentially what we're seeing, and you can even see it when it like flips and flies, is that the molecules of air in our atmosphere is what's determining its motion. And so now let's watch what happens again when we put the piece of paper on top. So you're putting the piece of paper on top of the textbook, thereby essentially blocking the air from interfering with the motion of the feather. And so if Galileo is right, they should both fall at the same rate. If some of our more instincts are right about mass, then we'd expect the feather to fly away. And notice they are falling together. It's right on top. Only at the very, very last second does the book kind of turn to the side and it floats just a tiny bit, but it's still falling at that same speed clearly. And so what we have shown is in fact that Galileo is correct. All objects are acted upon equally by the acceleration due to gravity, regardless of their size, shape, or mass. And so now we're ready to try our very first example of free fall. Of course, we've done questions already in the horizontal direction. It's not much different than that, but what I've done is I've, for your convenience, rewritten our one-dimensional kinematic equations in the y direction. Now, I mean, it's completely unnecessary, and you wouldn't need a formula sheet that had the equations in the x direction, and the y direction, etc. They're the exact same equations, but it's just handy to have here, and so There you have it, where our first equation again gives us a relationship between our final velocity, our initial velocity, acceleration, and time. Second gives us our position, initial velocity, acceleration, and time. And the final one is a combination of our two velocities, our acceleration, and again, our initial and final position. And so that's what we'll need to answer any of our free fall problems. And so let's jump in with a relatively straightforward question to get us started. Let's ask the following. Let's say we've got ourselves a cannonball, and we're going to shoot it straight up. From the ground with a speed of 250 kilometers an hour. All right, our first part of the question, the one we'll focus on first, is how high did it go? That's it? This is it? This is an entire problem? I've given you one value, 250 kilometers an hour. How are you supposed to solve a kinematic equation with so little information? Certainly, if this was a problem we were doing in the horizontal direction, you would look at that right away and you'd worry that you just didn't have enough information to do the problem. But don't forget that we know one extra bit of information when we're dealing with free fall problems, and that is, of course, the acceleration due to gravity. Even though this cannonball is shot straight up, the acceleration of the cannonball after it has left the cannon is due to gravity only. And that's what we're looking at here. We know its initial velocity when it gets launched, but any change in velocity has everything to do with the gravitational acceleration in the downwards direction. And so we actually know two things. We're like, okay, you know what? I know its initial velocity. I know its acceleration. It still doesn't seem like a lot of information. Okay, what else could we know? I want you to think of that as I start to set this problem up. And again, all of these examples you should be doing with me. Try to stay a step ahead of me and check your work as I go. So I'm going to start by visualizing, modeling and visualizing the problem here. Let's say that this is my cannonball at the beginning of this problem. Let's say y initial. And eventually, it's going to get here. Now after that, it's going to fall, but that's my kind of initial and final position in this part of the problem. And it is useful for me at this time to set a positive or direction for the y direction. Whether I choose y positive up or y positive down, it doesn't matter, but I have to make a choice so that the vectors in this problem, the velocity, the displacement, the acceleration, can have the right sign when we're doing the problem. And so I choose positive y up. Why? Because I always do. I'm used to it. I'm used to handling that. And I do recommend some level of consistency. What you do choose to do, do it. Do it all the time, certainly very often. And the other thing that I'm starting to make a habit of, which I intend to continue, is that I'm going to put my initial position at 0. That initial position of y initial equals 0 will allow me to do everything relative to that. And that makes sense. It's the ground. It's where I'm starting the problem. Very logical. Now let's write down some of the other values that we've had. We talked about v initial equal to 250 kilometers an hour. Now, again, I highly recommend doing some really good bookkeeping here by separating your x's and your y's. I'm going to call that v initial y. And we notice something very quickly, that is not in SI units. Kilometers an hour is easy to understand unit, but it's not the one we use for our problem solving. And so we're going to change this. Doing your typical unit conversion, we will get 69.44 meters per second. If you're having trouble doing that conversion, please look at a previous video. In fact, the first one. And so our next bit of information we have is our acceleration. We had that the acceleration was equal to 9.80 meters per second squared. How does that look? Everything look okay so far? No. There is a mistake that I've made on purpose, and it's this one right here. These quantities, these velocities and acceleration, they are vectors. And if I said plus y was up, then the acceleration is negative because it's downwards. On the other hand, my initial velocity was upwards, and so this one is positive, though we don't usually write the positive. Okay, so I've got some values now, my y initial, v initial, y, ay, it's not enough. There's one more piece of information I need so that I can eventually solve for my unknown. I'm asked to find how high it went, which is its maximum height. Well, what do I know about an object at its maximum height? If I throw this cannon up in the air, what's its velocity at its maximum height? Even though it's not given in the problem in any sense, you should be able to figure out that when an object goes up to its maximum height before it's about to turn around and head back down, its velocity is 0. All right. And so let's add that last piece of information, and we are ready to go. And so notice once again, we consider what we have, what we're looking for, and the most appropriate equation to solve this problem. Quick scan. I don't have any time information, nor am I asked for time in this problem. Look at my equations. I notice equation 3 does not have time in it as well. It has all of the terms I either have or I'm looking for, and so I will select equation 3 to finish this problem off. Highly recommend you pause the video at this time, using equation 3, solve for y final. Okay, hopefully you gave that a shot, and we can finish it up fairly quickly by writing our equation number 3 out. I'm going to write it the other way. Let's say VFY squared equals V initial y squared plus 2ay all multiplied by y final minus y initial. And as I've always recommended, let's keep the letters until the very, very last step. But if something is equal to 0, get rid of it now to simplify your algebra. So final velocity was 0, as is per usual. Our initial position equal to 0, leaving us a much, much simpler equation of just 0 equals v initial y squared plus 2a y final. All right. So keeping in mind we're looking for y final, we move our v initial y squared to the other side. And solve for y final. And so we can write y final if we divide both sides by 2a, and we'll just flip sides. It's totally a good move to do. You can think of it as multiplying or dividing by itself, but basically what we're doing is we're just moving one to the other side and the other to the other side, and we are left with y final equals negative v initial y squared, all divided by 2a. Here we go. And so with that equation there, all we have to do is to substitute in our numerical values. And so we had minus 69.44, and that was in meters per second. We're going to square that and divide it by 2 times negative 9.80. All right, everything's in SI units. You can check your units if you want to make sure they come out to meters, but I'm confident because everything's in SI units, throw it into my calculator and see what I get, and then let's assess that number to see if it makes sense. The first thing I'll expect is a positive number. If we said plus y was up and I started up the y equals 0 on the ground, I'm going to expect a positive number. I think it's going to be pretty big too, right? That cannonball was moving super fast. How high did it go? Well, a staggering height of 245.7 meters. That's what my calculator is telling me. But of course, we have to put our final answer into the proper amount of significant figures. And I believe that the only thing we're given is our speed, 250 kilometers an hour. The 0 is not significant, leaving us with 2 sig figs. And so we will write y final as 250 meters. Oh wow, coincidentally, kind of, it ends up with exactly 250 meters. Excellent. All right. So not too bad. Let's try something a tiny bit more challenging. Part B, and so same question. Everything we've done so far, or were given, I should say, in the original question is cool. But now I'm asking a question: how long? And I'm not going to make it so easy, like how long does it take to get to the maximum height? It was a totally legitimate question. You could ask, and feel free to do that if you want. But I want to do something a bit more exciting. How long does the cannonball take to get to a height of 32 meters, 32.0 meters. Actually, we don't even need the 0.0, right? Because we're doing everything to 2 sig figs. 32 meters above the ground. That's it. All right, so it's a different problem. We can't necessarily use the information that we calculated in part A. Certainly we can't use y final, because now we're talking about the cannonball not at its maximum height, but just 32 meters, hardly anything compared to 250 meters, hardly anything off of the ground. And we want to know the amount of time it takes to get there. And so let's set up our problem again. This time, much smaller height difference between our initial position, y initial, I'm going to call it 0 one more time, and our not final position, but our specific position, which I'm just going to call y2. I'll make that 32 meters. Again, I'll set plus y up. Again, the acceleration due to gravity in all of these problems is negative 9.80 meters per second squared. It will always be that for any object near the surface of the Earth at any point in its travels, up or down. And finally, our initial conditions must still be the same. We still have our initial velocity in the y direction of 69.44 meters per second. And we are going to use, we don't know what the speed is, right? So we don't have our speed at y2, but we're not asked to find it, nor do we have it, and so it's time that we're looking for. How long does the cannonball take to get to that specific height? All right, so let's go ahead and choose an appropriate equation that is going to have all of those factors in it. Y initial, y final, acceleration, initial velocity, and time. No final velocity this time. Going back to those equations, the clear answer is, of course, number 2, the second equation. So pause your video again, go ahead and grab that second equation and try to solve for the time. All right, so for those that are back from solving this equation, let's see how you did. Now, Not as easy as part A, certainly, and so you may have got stuck, and there's no shame in that. Our equation is that y2 equals y1 plus v initial y times t plus 1/2 at squared. All right, let's zero our zero terms. And we only have that. Ooh, that's not much. That's not much at all. And so what kind of equation do we realize we have? Well, we have some number by itself, some number in front of a t. Now remember, it's t that's the unknown. This is the unknown. We know what these guys are. We know what this is. We know what this is. And so when you have a question of this form, this is called a quadratic equation. And I'm sure that you've all seen the quadratic equation before in mathematics. And so I'll just do a quick side note to remind us, but if you need more work on the quadratic equation, feel free to ask me for further guidance. But essentially, you know that the quadratic equation, we need for the quadratic formula, or let's say we need to solve a quadratic formula. And so t is equal to, you know what, let's write it the other way around. So the general form of the equation, a quadratic equation, is that 0 equals at squared plus bt plus c. Just put that behind it. And so if you can write your equation in this form, where a is a constant, b is a constant, c is a constant, and t is our unknown, then you can use the following equation to solve for it. It is a difficult equation to solve because you will get two answers. So you have to be very, very careful applying this. T is going to be equal to minus b plus or minus the root of b squared minus 4ac all divided by 2a. And so all you have to do is substitute your values in. So basically you write your equation like the quadratic, then you take your a, b's, and c's, you put them into this equation, and you're going to get two answers. That's what the plus and the minus is for. One of your answers has the plus in it, the other answer has the minus in it. You get two numbers, and then you have to decide which number is correct. If you need one answer, one is right and one is not right. There will be times where both could be correct as well, depending on the nature of the question itself. And so let's go back to equation 2 and rewrite it in terms of the quadratic equation. And so we can go ahead and rewrite equation 2 again. This time I'm going to, well, let's just write it as we saw it before. 1/2 ayt squared plus v initial yt minus y final equals 0. And so clearly in the way that this is written, 1/2 ay is a. Again, please note that these ABCs up here are just random letters used to talk about any constant. They don't have a physical meaning. They're math variables. And so that a is not this a. This a, of course, is acceleration. Another good reason to keep the y on it. And so we have a is 1/2 times the acceleration, b is just v initial, and c is equal to negative y final. Be very careful about the negative. And so we need some numbers now. And so while I have always said don't put your numbers in right away, now is the time to write this as minus 4.9 t squared plus, what did we say, 69 point, was it 44, something like that? Yep. And that's times t, and this is plus negative 32. So it's minus 32. All right, throw that into your quadratic equation and find out what the times are in this case. Pause the video if you need to. The answers that I get are the following. The time is equal to 0.477 seconds and 13.7 seconds. Which one is correct? Which of these two numbers is right? Well, let's remind ourselves what the question was. The question had asked, how long does the cannonball take to get to a height of 32 meters above the ground? It didn't say on its way up or on its way down. So the correct answer is actually both of them. What these two times indicate are the following. We've got this cannon and it's launched. It reaches 32 meters here in 0.4777 seconds. And it keeps going up, 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 hits its maximum height of 250 meters above the earth. And then it starts coming down faster, 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 faster. And it hits 32 meters again on its way down. The position is 32 meters, both on the way up and on the way down. That's how the position works. And so at 13.7 seconds, it's now 32 meters above the ground as it's coming down just before it hits, I guess it hits the cannon that launched it. And so the way this was worded, both of these answers are the correct answer. So be very careful looking at what you want in these sorts of cases. Sometimes you'll do the quadratic equation and you'll actually get a negative value for one of your answers, and then it's very, very clear that the other is the correct answer. All right, so to 2 sig figs, there we go. So, in the previous videos, we talked about motion in the horizontal. We talked about motion in the vertical. The kinematics of going up and down, the kinematics of going left and right, they're well understood. And so you might say to yourself, I guess we're done kinematics. But no, there's one dimension we haven't talked about yet. What is that dimension that we're looking for? It's actually on a plane. It turns out that if one is moving essentially diagonal at some angle of inclination to our regular y and our x axes, it's still one-dimensional motion. We're not talking about traveling through the air at an angle. That, of course, is not one-dimensional motion, as we'll see in a future video, but one-dimensional motion along a plane, along a straight plane, where you're stuck to that plane or that slope or that angle, that is still one-dimensional motion, and it can be handled just the same as we've done so far, with one just little tiny change. And so if we have a mass that's on a plane, let's say we take this little cap cover right here, we put it right there, and we just have it on a horizontal surface, it's not naturally going anywhere. It doesn't have an acceleration due to any natural thing like gravity. But if we put it slightly higher, then it's a component of gravity starts to act on it. And at some inclination, the gravitational acceleration is enough to drive that thing downwards. Now, clearly, if we had a higher inclination, let's say that the book was inclined, we'll just do the whole thing, at a very high angle, then we'd expect our cap to move considerably. At a very low angle, it'll move a little more slowly. And so it seems like the angle of inclination is going to determine what component of gravity is acting upon our mass. And that's what motion on an inclined plane involves. It's just a tiny bit more complicated than our free fall problem, because all of our motion is due to gravity, but it's due to a component of gravity. It's not due to the entire 9.80 meters per second squared. The acceleration is going to be some fraction of that. And so let's take a look at this. I'll draw our incline here. we'll put a mass on top of it, and this mass is accelerating downwards. We all know that naturally that our block on that incline will accelerate down our ramp, and the acceleration is going to be dependent on that angle. And so we measure our inclination always from the horizontal. This is 0. This is 90 degrees, straight up and down. And so any angle above that is going to be the angle that is going to determine how much of the acceleration due to gravity plays an important role. And so please note that this motion is still one-dimensional motion. It looks like it's moving in 2 dimensions. If you put your axes in our typical kind of y and x way, yeah, absolutely. It's not going in the y, it's not going in the x. There's some component of motion in both of them, but you don't put your axes like that. It's illogical to. If the acceleration of this block is in the downward direction, that is down along the surface of the ramp, then it is imperative that you also set your axes there. This is my axes. I'm going to call that the S direction. And down the ramp is the positive S direction. This is just an arrow indicating motion. This is the arrow indicating the axes that I'm going to use to solve my problem. So this motion is still one-dimensional motion, and as long as the axis is set for the direction of motion, it is one direction. And so that's what we've done. As long as the axis is set for the direction of motion, we have one-dimensional motion. And so don't call it X, don't call it Y. When you're on an incline, S is good, R is good. Don't use D as well. And so the only thing left for us to be able to actually solve kinematic problems up and down a ramp, because don't forget, if I took that block and I pushed it up the ramp, it's going to go up the ramp initially, slow down, stop, come back down, and slide faster and faster down the ramp, just as if we threw something up in the air. We want to know what the acceleration is. What is the acceleration down the ramp? What is this AS? So, acceleration down an inclined ramp or plane, whichever you want to call it, is dependent on gravity and one more thing. Obviously, the acceleration due to gravity is important, but it's a mix of that and the angle. Of the incline. A combination of which gives us our acceleration. And please note that this term here is going to be used for our angle. It is the Greek letter theta. Let's write it over here on the side. That is theta. It's used very often as a stand-in for some kind of an angle. And our acceleration, at least the magnitude of our acceleration, is g sine of theta. And if we had down the ramp as positive, that would be a positive value. If it, up the ramp was positive, that would be positive. And that's it. We've got A is equal to g sine theta. Now let's appreciate what that actually means for various angles. Remember that we're measuring our ramp from the horizontal. And so at the horizontal, this component here, theta, is going to be 0. So g sine of 0, where the sine of 0 gives me 0, gives us a total of an acceleration of 0. So if you're at a horizontal surface with no inclination, clearly your acceleration due to gravity is nothing. On the other hand, what about the other extreme? What if we turned our ramp suddenly and it was vertical? Well, then that angle would be 90 degrees. And so sine of 90 is 1. And sine of 90 degrees being 1 gives us an acceleration of g, an acceleration of gravity itself. Those are the extremes. Those not really inclination at all. But anything in between will get us closer and closer to that. So a small angle, a slow acceleration. A large angle, a much faster acceleration. And that's all we need to do one-dimensional kinematic problems on a slope. The method after you've calculated the acceleration is exactly the same as it is for horizontal motion and for vertical motion.